Hi everyone, welcome back to Dave's Math channel. Today I'm going to do another video on geometry. This one I'm going to talk about elliptic curves. You might have heard of these. They're very important curves with a lot of applications. Anyway, let's just get started. So, what is an elliptic curve? Well, the technical definition is pretty complicated. Elliptic curve is technically a curve of genus 1. And that's kind of a strange definition. Maybe just to give you some idea what that means, what's a curve of genus 0? Those are the simplest curves. Those are just lines and conic sections. And we know pretty much everything about those curves. And if you're working over the complex numbers, then it turns out these curves really look like surfaces because complex numbers have two coefficients, a real and an imaginary part. And so remember that a curve has two variables. A curve over real numbers has x and y coordinates. That's also true of complex numbers, except now x and y are complex, which means both x and y have two coordinates now. So a curve a curve over the real numbers is one-dimensional, but a curve over the complex numbers turns out to be two-dimensional. And you could talk about the topology of a two-dimensional surface. And the simplest topology of a two-dimensional closed surface is a sphere. A sphere is just like a ball. And I don't know if you guys know anything about topology, but topology doesn't care about the exact shape of a surface or a curve. It just cares about kind of its properties if you don't tear it. And so you can deform a ball into an arbitrary blob, and it still has genus 0. The genus is just really the number of holes a surface has, closed surface. Holes sometimes are called handles. So a sphere has no handles or no holes, but a genus 1 surface has one hole, so it's like a donut, a torus, or like a coffee cup. There's a joke among topologists or among mathematicians that a topologist is a type of mathematician that can't tell the difference between a donut and a coffee cup. And the reason they say that is because both a donut is surfaces. Both the surface of a donut and a surface of a coffee cup, they have the same topology. They're both surfaces with one handle. So you can continuously deform a donut into a coffee cup. But anyway, they look like elliptic curves too, over the complex numbers. That's a pretty technical definition. And if you want a more algebraic definition, a more down-to-earth definition, remember that in the last video a couple days ago I talked about conic sections. Those are just quadratic curves, curves that are defined by polynomials and two variables of degree 2. In the same way, elliptic curves are polynomials defined by polynomials of degree 3. So sometimes they're called cubic curves. But I think the name elliptic curve is a very unfortunate name. The reason it got that name, they really have nothing to do with ellipses. And I think a lot of people get confused between ellipses and elliptic curves. They're about as similar as Java and JavaScript, which are two completely different programming languages. And the reason they're called elliptic curves it's a historical reason. Because in the 19th century, there were some mathematicians who were trying to find a formula for the arc length of an ellipse, which is a very complicated calculation. But it turns out that you can actually find an analytic expression for the arc length of an ellipse in terms of these special functions called elliptic functions. And they were called elliptic functions because, as the name implies, they give you the arc length of an ellipse. Well, it turns out that elliptic functions are also very closely related to elliptic curves. So that's how they got their name, which I think is a very unfortunate name. It'd probably be better if they changed the name to something else. I don't know if they will because they're used so commonly now. It's kind of become a standard name. But just remember, they're basically cubic curves. And there's an important form of elliptic curves. You don't have to write it as an arbitrary cubic. It turns out as long as it's an elliptic curve over the real numbers or the complex numbers, you can always write in what's called Weierstrass normal form. And that's a much simpler form. And Weierstrass normal form is y squared equals x cubed plus ax plus b, where a and b are constants. And the only requirement on a and b is that the discriminant, this quantity 4a cubed plus 27b squared, that cannot be zero. It turns out that if the discriminant is zero, you don't really have an elliptic curve. You have a curve with a cusp. It's a singular curve, and usually people don't regard those as elliptic curves. They're not very easy to work with. So elliptic curves, you always want the discriminant to be non-zero. You don't care if it's positive or negative, but it should be non-zero. So anyway, that's the Weierstrass norm. It turns out that you can get every elliptic curve, every cubic curve can be converted to Weierstrass normal form by a linear transformation, a linear change of variables. Sometimes that's called an affine transformation. So, something like x prime equals ax plus b, ax plus by plus c, and y prime equals dx plus ey plus f. Here, A and B are different than the ones I wrote down here, but you can always do that kind of transformation to get any cubic curve into this Weierstrass normal form, which we usually call an elliptic curve. Usually when you're working with elliptic curves, they're usually given in Weierstrass normal form. Anyway, and here's some pictures. I mean, you might be wondering what these elliptic curves look like. These are all pictures of elliptic curves given in Weierstrass normal form. Actually, the three on top are elliptic curves. The two on the bottom are singular. You can see that both the ones on the bottom have cusps. The discriminant is zero for both of these. So, a very simple case of a singular elliptic curve would be y squared equals x cubed. Here you just have a equals b equals 0. And you can see there's a cusp at the origin. And sometimes a cusp is like a crossover point. You can get kind of interesting looking singular elliptic curves that intersect themselves. So here's an example on the bottom right: y squared equals x cubed plus x squared. That also has discriminant 0, and it's a nice smooth curve, but it intersects itself. And we don't want that. We don't want to work with elliptic curves that intersect themselves, because those are also singular. But what else can we get? Let's look at the pictures on top here. These are more generic examples of elliptic curves. And there's sort of two different kinds of elliptic curves. There's ones that have one piece, and there's ones that have two pieces. And the first two of these have one piece. I think the one you usually see most often looks like the one on the top left. I guess for this example, y squared equals x cubed minus 3x plus 3. So a is minus 3 and b is 3. And then you get a curve that looks like this. You can calculate its discriminant. It turns out to be 2160. In this case, it's non-zero, which is why it's not singular. And then the second example is y squared equals x cubed plus x. And again, this has one piece. And this one happens to have a negative discriminant. But then the third one has two pieces. This is y squared equals x cubed minus x. And the piece on the left, I think sometimes people call that an egg, or the egg of the elliptic curve. And then I don't know what they call the piece on the right. I guess the other component. But it's usually pretty easy to see how many pieces an elliptic curve has. I mean, if you factor x cubed minus x, that's like x times x minus 1 times x plus 1. So it's pretty easy to see that this elliptic curve has three x-intercepts, negative 1, 0, and 1. And it has two pieces for that reason. Whereas the other two just have one x-intercept. So anyway, that's just some pictures. And why do we care about elliptic curves? You might be wondering this. I mean, why go through all this trouble to study these things? They're pretty complicated. Well, it turns out the main reason we're interested in elliptic curves, and I think this is a really fascinating reason, actually. It turns out that you can turn an elliptic curve into a group. And if you don't know what a group is, maybe you might want to watch some of my videos on group theory. I have a series of videos on group theory, or you can just look up group theory. There's plenty of references on the web. Groups aren't really all that complicated. And there's two types of groups. There's abelian and non-abelian groups. Abelian groups are the simplest ones. Those are just ones where the group operation's commutative. And usually we write those as additive groups. So usually for an abelian group, our group operation is usually called addition. And it turns out that we can add points or subtract points, if you like, on elliptic curves. So the elliptic curves are kind of endowed with this arithmetic, this group arithmetic. And so, in order to make a group out of an elliptic curve, you have to first define how to do the group operations, which are really just negation and addition. So negation is easy. If you always want to start with an elliptic curve in Weierstrass normal form because that makes them a lot easier to work with. So let's assume we have an elliptic curve in Weierstrass normal form. That would look kind of like the picture on the right. This is just kind of a generic example of a elliptic curve in Weierstrass normal form. It's always symmetric about the x-axis. That is one property I don't think I mentioned about elliptic curves in Weierstrass normal form. They're always necessarily symmetric about the x-axis. And there's one other fact I forgot to mention. If you want to make a group out of an elliptic curve, it's not just enough to just use the points on the curve. You have to use one more point. The point at infinity, we call it. I mean, that's a little bit weird. Usually what you're doing here is you're doing what's called projective geometry. You can actually, in projective geometry, you can think of the point at infinity as another point. Kind of a weird thing. I don't want to go into that in more detail. But there is a point at infinity. If you think of this elliptic curve in projective geometry, it does have a point at infinity. And that is the identity element of the group. You usually call that O, which stands for 0. It's like the 0 element. It's the identity element. And since it's an additive group, you can think of this element as 0. It's the element 0 of the elliptic curve, which is a little ironic because 0 is at infinity. you know. But anyway, that's just the way things work with elliptic curves. So how do we negate? How do we negate a point on an elliptic curve? Well, let's look at this point R. Forget about the addition right now. You see the point R, there's P, Q, and R. R is the point in the fourth quadrant, the lower right. They say R equals P plus Q, but don't worry about P and Q for now. Let's just look at R. How do we negate the point R? Well, that's easy. All you have to do is you look at the vertical line that intersects the elliptic curve, and then the other point. There's always going to be one other point, and that's minus r. And it's always the same distance above the on the other side of the x-axis. So all we're really doing is negating the y-coordinate. So if r has a coordinates x comma y, then negative r has a coordinates x comma minus y. And r could have been in the top. It doesn't matter what quadrant r is in. If r has coordinates x, y, then it's negative has components x, y, minus y. That's true for every point on the elliptic curve. Some points are their own negative. Like if you look at the point on the left, they don't mark it on here, but if you look at the point on this curve, the leftmost point, which they don't mark, it's kind of near P, a little bit above P, but it sits on the x-axis. Well, that point is its own negative, because if you reflect it about the x-axis, you get back that same point. So that's fine, because that just means if you double that point, you get the point at infinity. Because a point if you double it, you get 0. Remember, 0 is the identity element of the group. Well, I don't want to go into some more detail, but it's equal to its own negative. You'll have to trust me on that. And I didn't talk about how to add 2 points yet. That's the other thing we have to know how to do. Well, adding 2 points is pretty easy too. What you do is now we want to look at these points P and Q. So P and Q are supposed to be sort of 2 arbitrary points on this elliptic curve. Well, it turns out that whenever you have 2 distinct points on any elliptic curve, you can always draw a line connecting those 2 points, and it turns out that line always intersects the elliptic curve in a third point. So this third point we're calling minus r here. And why are we calling it minus r instead of r? Because there's one other operation we have to do if we want to add p and q. First we find the third point, and then we negate that point. So it turns out that the p plus q is the negation of the third point on the line that connects p and q. Or if you like, there's sort of two things you do. First, you find the third point on the line connecting P and Q. Then you find the second point on the vertical line with that third point. And that gives you the sum. That's how you add 2 points on an elliptic curve. That's if they're distinct. And you have to do something a little bit different, kind of similar. If P and Q are the same point, what if you want to double an elliptic curve point? Like, say P equals Q and you want to find 2P, which is really just P plus Q. Well, what you do in that case is you have to first start with a tangent line. So, since elliptic curves are smooth, continuous, it turns out that there's always a tangent line. That's a line that just touches the elliptic curve, doesn't intersect it at any other points. But then you extend the tangent line, and it always turns out there is another point on the elliptic curve that intersects that line, and that line, and then you have to negate that line again. That's going to be your point minus 2p. You negate that point, means you just find the second point on the vertical line again with that point, and that second point is minus, or no, it's p plus q. It's 2p. So if you like, the second point on the same line is minus 2p. So that's how you do group. That's how you do the group operations with the points on an elliptic curve. I didn't prove this is a group. It's pretty complicated to prove this actually is a group. You have to show that it satisfies the 3 axioms of a group. The hardest one to prove is associativity. I'm not going to do that. But anyway, that they do form a group. And the fact that they form a group, actually, that means that they have a lot of very useful applications. And one application is cryptography. This is a pretty new area of research right now, actually. A lot of people are interested in elliptic curve cryptography right now. Because right now, the most commonly used crypto system, the one that I think protects all your bank information and all your passwords, that's what's known as the RSA crypto system. And that involves the difficulty of factoring large numbers. I mean, usually they use really big numbers with about 300 digits, which no computer in the world with any known algorithm today can factor within the age of the universe. That's why all your secret information is secure, at least for now. But I think one thing a lot of computer scientists are worried about right now is, it's conceivable that, maybe we just haven't discovered an efficient method for factoring large numbers. Maybe there is one that'll make RSA obsolete. As a matter of fact, with quantum computers, there already is an algorithm that can factor, at least in principle, factor large numbers very, very quickly. And if quantum computers are still kind of in their infancy, but there are predictions that in another 20 years or so, we'll have quantum computers that are powerful enough to break RSA. And the good news about that is that there'll also be new crypto systems that actually work with quantum computing that will make these new factoring algorithms secure. It won't be able to break these codes, but we'll have to overhaul RSA before that happens. And I guess that's going to be a major job, overhauling RSA with a quantum algorithm, for encryption. But sort of an intermediate step would be to use elliptic curves. It turns out that there's also known crypto systems that rely on elliptic curves rather than factoring large numbers. And these are a lot more secure. Nobody's figured out how to break these crypto systems efficiently. So I think right now a lot of cryptographers are working on I guess at least in some areas, replacing RSA with these elliptic curve crypto systems. Which I think is pretty exciting, actually. And there's also things called elliptic curve Diffie-Hellman. I'm not going to go into this in detail, but there's a thing called the Diffie-Hellman protocol. This is kind of related to cryptography. I mean, I guess it is, but it's not really for like making secure for protecting information. It's more used for communication. If you want to have two people, Alice and Bob, be able to communicate with each other over an insecure channel, they can do this using what's called the Diffie-Hellman protocol. And it has a lot of other applications too. Like you can have a group of people playing a game of poker where it's an exclusive group and nobody else can join in unless they explicitly join it. So it has useful applications, and I guess there's an elliptic curve version of this. So I just thought I'd mention that. And another application is factoring. Actually, it turns out there's an algorithm for factoring large numbers, and this was discovered by my former thesis advisor, Hendrik Lenstra. This is probably the thing he's most famous for. It's called the Lenstra's elliptic curve algorithm. I think he discovered this algorithm in the 1980s. He once told I had a class with him, and he once said in one of his lectures, he said that if he had a penny for every number that got factored with his elliptic curve algorithm, he wouldn't be there. He'd be like a billionaire. So I guess it's unfortunate that didn't happen. But anyway, it is a very fast factoring algorithm. As a matter of fact, along with a number field sieve, I think the quadratic sieve and the number field sieve, if you combine those two or three factoring algorithms, that gives you the fastest known way, at least classical computation, fastest known way to factor large numbers. Still not fast enough to break RSA, but it's pretty fast. I think number field sieve now they can factor numbers with about 150 digits. But anyway, I just thought I'd mention that. So anyway, that concludes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.